Moritz Scherer from ETH Zürich, and he's going to talk about CUTIE, beyond POPs per watt ternary DNN acceleration. And this obviously has connection to this morning's keynote talk. So Moritz, you have the stage. Thank you.
Yes, thanks for the kind introduction, Boris. Again, my name is Moritz. I'm a PhD student with Luca Benini's group in Zurich, and I have the pleasure of talking about CUTIE, the completely unrolled ternary inference engine today, which is the ternary DNN accelerator we have been working on in ETH. So let's set the stage a bit by talking about why we care about energy efficiency and tinyML in the first place. I guess as most of you are aware of, if we are looking at battery-based applications, we typically deal with a power envelope of single-digit milliwatts, and for energy harvesting systems, it's even less. We are typically talking about hundreds of microwatts there. And in terms of memory, we have to deal with hundreds of kilobytes in normal use cases. And to deal with these kinds of hard constraints that we cannot yet work around, we typically use ultra-low precision quantization for our networks. So the previous speakers have mentioned 8 bits and lower. Some have even talked about binarized networks, and we've seen that we can optimize the energy accuracy trade-off by using fixed point and sub-byte networks, and even go as low as binary neural networks. But for all of them, the key to really making the most of this lower compute complexity is proper acceleration, which is the topic of my talk today. So the textbooks, the state of the art is kind of the systolic array, which scales to many chip systems. It's designed for flexibility and heavily pipelined. But there again, we see that most of the energy is still not spent on computations. So we see huge overheads in clocking and data movement, and the core computational energy is usually between like 10 and 30% when we account for pad energy and so on. And all of the rest is memory access, data movement, and control. This brings me a bit to the motivation. So we asked ourselves the question how we can maximize this energy efficiency and low power digital CNN accelerators at the architectural level. And the first point is to really minimize the ether movement. So we aim to keep weights and partial results local to our compute units. We try to maximize computational efficiency by using ultra-low precision operands, by using a completely unrolled and parallel architecture, hence the name CUTIE. And we aim to minimize itching activity, also by leveraging the irregular sparsity that we get from sparsity-aware training, and by introducing this sparsity by using ternary weights and activations instead of binary ones. So by combining these three key ideas, we are able to present today the completely unrolled ternary inference engine, and which achieves around 2 petaops per joule in average energy efficiency. And I'll go right ahead with a deep dive on the computational core. So what you see here is a typical CNN flow. So we have kernel windows that go into the compute core, and we only target layer by layer execution here. We keep all of the weights for a layer in a localized ledge-based buffer, and we just multiply and add the activations and weights. But we do this again in this completely unrolled architecture. So we actually multiply and add all values in one cycle instead of doing any sort of iteratively decomposed multiply and accumulates. And in this way, we are able to fully leverage the zeros in the weights to reduce switching activity in the pop counts. We then add support for pooling. So this is a like parallel hardware block that we can also turn off if we don't need it. And finally, we add this thresholding stage that reternerizes the results with dual thresholds, which is equivalent to any requantization algorithm you might be familiar with for higher precisions. When we zoom out a bit from the compute units for a more complete view, we can see that we have a number of OCUs there. So we replicate them by the amount of channels we would like to support. And we add a tile buffer, which allows us to extract the maximum amount of data reuse for our convolutional layers. We use a compressed ternary storage. So we add compression and decompression stages. And this minimizes the required memory to 1.6 bits per operand. We introduce some very light pipelining. We really try to keep everything as close to combinational as possible, again, to minimize overheads. And we reuse those registers to silence unused units. And finally, we add dedicated weight and feature memories, which are large enough to store the worst case feature maps and weights. And this is basically because, as we've seen in the other talks, I/O is extremely expensive on this scale of computation. So we try to minimize it. Now for some implementation details. So the architecture is highly parameterizable. We can choose the number of supported channels, kernel shapes, pipeline depth, memory sizes, and so on. And for this sake of evaluating it, we chose an implementation with 128 channels, 3 by 3 kernels, and a 32 by 32 pixel feature map support. And we evaluated a pretty standard 9-layer convolutional neural network that we trained with our own sparsity-aware method. And this results in some very nice numbers. We see that in 7 nanometer technology, we are able to achieve a sustained average energy efficiency of the core. So this is about I/O of around 2.1 petaops per joule, a peak energy efficiency of 3 petaops per joule on an area of around 1.2 millimeters squared. We are able to outperform in state-of-the-art binary accelerators, both in terms of accuracy and energy per inference by a significant margin. And we can even clock this highly pipeline design at a reasonable rate of 66 megahertz, which, as you can see, is not really required since the FPS is quite high. So for the insights, we really saw that using ternary weights and activations over binary weights and activations can help to reduce energy by a large amount, as well as increasing accuracy for ISO architecture networks. And this leads to around 5 times lower energy per inference at the same accuracy. We also see that this fully unrolled paradigm leads to significantly less data movement, and the spatial smoothness that is inherent to many data sources is really helpful to reduce the switching activity as well. And we really see that training is an important factor in the efficiency of our accelerator. And my final words are, if you're interested, please check out our paper on arXiv or email me, and stay tuned for our tape out in a 22 nanometer technology. Thanks.
Thank you very much, Moritz. Thanks for this nice presentation. I see no questions on the live forum, but I guess I can ask you one. So this network you use to benchmark, this is essentially your own network. It looks like a VGG type, very regular network. Can you talk a little bit about more irregular networks and how they would do on your platform?
Yes. So the main idea for the evaluation we did was to see how far we can go with very sparse network and the influence this sparsity has in this, let's say, unrolled architecture. We have also tried with ternarized mobile net-like architectures, but they typically fare less well, since when we really limit the precision, we observe that we need more of a dense basic structure to compensate for the loss in precision.
Okay, that makes sense. Thank you very much.
I'd like to acknowledge our sponsors. First, it's ARM that develops software and hardware for tinyML. Qualcomm, Samsung. These three are the executive sponsors. And then followed by platinum sponsors: ETA Compute, Lattice Semiconductors, and the gold sponsors are BrainChip Corporation, Cisco, DSP Group, H Impulse, EMSA, Visual Sense, General Matter Labs, Green Waves Technologies, Hymex, ImagineMob, Latent AI, Maxim Integrated, Kixo, Reality AI, SenseML, Silicon Labs, Sentient, and Google TensorFlow. XMOS, and the silver sponsors are H-Cortex, HOTS, and SynSense. Again, we are very grateful for their continued support, and this is a great testimony that the foundation and this community is really of huge interest for the companies and for the whole world.